You know, it's funny how we're conditioned to think about space.
Yeah.
You go out somewhere, way out in the country, away from all the city lights. You look up, and what do you see?
Stillness.
Stillness, exactly. It's this, like, frozen, silent tapestry of light. It feels permanent, serene.
It is the ultimate illusion, though.
It really is, because if you actually peel back the data, and I'm talking about this specific stack of reports from, just the last week, early February 2026, that stillness is a complete lie.
Oh, absolutely.
We aren't looking at a painting, we are looking at a demolition derby.
A demolition derby where the cars are moving at relativistic speeds.
Right. So, welcome to the deep dive. Today, we are just tearing up that whole serene space postcard. We're looking at a universe that is spinning and crashing and racing way faster than we ever realized.
Yeah.
And the headline here isn't just that things out there are fast. It's that we, us, right here, might be moving way, way faster than we thought.
That is the big one. That revision to the solar system's velocity.
Yeah.
It's a real head-scratcher.
We are definitely going to get to that massive adjustment and what it means for our maps of the galaxy. But we've also got, asteroids spinning so fast physics says they should explode?
And stars getting evicted from their homes.
And black holes acting less like drains and more like engines.
It really has been a week of cosmic speed. The data coming out of the Institute of Cosmosciences in Barcelona, the new Event Horizon telescope updates, it all points to one thing.
Motion.
Motion is the dominant force.
So let's start small. And when I say small, I mean a rock the size of a suburban house. Asteroid 1998 KY26.
1998 KY26. That sounds so generic, just another catalog number, another rock in the pile. But this thing is a rebel.
So this was the report from November 2025. This rock is tiny, about 11 meters across?
Barely.
Usually we just ignore the small stuff unless it's, heading for our atmosphere. But this one is special because of how it moves.
Right. So for context, most asteroids are, they're leisurely. They just tumble slowly through the dark.
Wow.
But new observations on KY26 revealed it is spinning at a rate that just shocked the team. It is moving twice as fast as the previous models predicted.
Twice as fast? What does that even look like in practice? Like a spinning top?
Imagine a house spinning around completely end over end every 10 minutes.
Wow.
It's a hyperspinner. And this isn't just a wow, that's fast moment. It presents a genuine physics paradox.
Because of centrifugal force.
Exactly. I mean, think about a merry-go-round. If you spin it too fast, everything just flies off.
Sure.
In space, asteroids are rarely solid rocks. We call them rubble piles. They're just loose gravel and boulders held together by their own very weak gravity.
So if you spin a pile of gravel that fast...
It should turn into a shotgun blast. It should just fly apart instantly.
Yeah.
The fact that 1998 KY26 is intact while spinning this violently tells us our assumptions about its structure are completely wrong.
So it can't be a standard rubble pile.
No way.
Is it a monolith, then? A single, solid slab of rock?
That's the leading theory. Or there are cohesive forces, like Van der Waals forces, the same thing that let geckos stick to walls, that are actually strong enough in microgravity to glue this gravel together against that spin.
That is wild. Sticky gravel holding on for dear life.
Pretty much.
But this isn't just academic, is it? Because we're actually trying to go to this thing.
We are. The Japanese mission, Hayabusa 2. It's famous for bringing back those samples from the asteroid Ryugu a few years back.
Right.
Well, it's on an extended mission now, and KY26 is the target for 2031.
I have to imagine this new data complicates things for the mission control team.
Complicates is putting it mildly. The November report called it a massive challenge. Ryugu was big and slow. Landing on it was like docking a boat.
Okay.
Trying to interact with KY26 is like trying to jump onto a ceiling fan.
So how do you even land?
You probably don't land in the traditional sense. You do a touchdown operation, you sync your speed, you kiss the surface for a split second to grab a sample, and you get out.
But if the surface is rotating that fast beneath you?
The timing has to be perfect. If you're off by even a second, the asteroid itself just smacks you into orbit.
High-stakes tag in deep space.
Precisely. But if they pull it off, it answers that physics question. What holds the fast ones together? And that knowledge is crucial for planetary defense.
Oh, how so?
If we ever need to deflect a fast spinner heading for Earth, we need to know if it's a solid rock or a sticky dust bunny. The physics of the impact would be totally different.
Okay, so that is the small scale, a house-sized spinner. Now I want to zoom out to the neighborhood scale. Because while that rock is spinning, we are moving too. And this is the part of the research packet that actually made me stop and reread the sentence.
The Solar System Speed Revision.
Science Daily, November 22, 2025. Our solar system is racing through space 3x faster than we thought.
It is a jarring number.
3 times. I mean, we have maps. We have GPS for the galaxy, essentially. How could we be wrong about our own speed limit by 300%? That feels fundamental.
It's not so much an error as it is a change in perspective.
Hmm.
In space, speed is always relative. Usually, when we say the solar system moves at X speed, we mean relative to the center of the Milky Way, or maybe relative to the cosmic microwave background, the leftover heat from the Big Bang.
Okay, those are the big fixed mile markers.
Right. But this new study looked at our speed relative to the local interstellar medium, the clouds of gas and dust we are immediately plowing through.
Ah, so it's like measuring your speed against the water current rather than the riverbank.
That's a perfect analogy.
Ah,
And to measure this, they use something called muon flux anisotropy.
okay, I saw that term in the notes. Break that down for us. It sounds like, technobabble, but I have a feeling it's important.
It's actually really clever. Muons are subatomic particles. They rain down on Earth constantly, created when cosmic rays hit our atmosphere.
Right.
Now, if Earth were standing still in the galaxy, these muons would hit us evenly from every direction.
Like rain on a completely windless day.
Exactly. But because we're moving, we run into them. It's like driving a car through the rain. The front windshield gets soaked. The back window stays relatively dry.
So we just look at which side of the Earth is getting wetter with muons.
Yes. That wetness difference is the anisotropy. By measuring exactly which direction the muons are coming from and how hard they're hitting, we can calculate our velocity vector through the local cosmic rays.
And that calculation is what jumped up by 300%.
It suggested that when you account for all the local flows of gas and dust, our relative interaction speed is way, way higher. We're essentially hitting the local interstellar medium with 3 times the force we anticipated.
So does this change anything for us, down here on the ground? I'm not going to spill my coffee because of this, man.
Yeah. No, you won't feel the G-force,
Yeah.
but it changes our understanding of the heliosphere. That is the magnetic bubble the sun blows around us. It protects us from the worst galactic radiation.
It's our shield.
It's our shield.
Yeah.
And if we're moving 3 times faster through that interstellar medium, the pressure on the nose of that shield, the bow shock, is immense. It's much more compressed than we thought. It means the barrier between us and deep space is thinner, tighter, and under way higher stress.
We're driving the boat faster, so the wake is more violent.
And that affects how we interpret every bit of cosmic data that comes in through that shield. It's a fundamental recalibration of our place in the neighborhood.
Speaking of neighborhoods and things moving fast through them, let's talk about the neighbors that get evicted. You flagged a study from February 4th about runaway stars.
Yes, from the University of Barcelona. This is the most extensive census ever taken of these objects.
I love that term, runaway star. It sounds almost romantic. But the physics behind it is pretty violent, isn't it?
It's extremely violent. These are massive stars, way, way bigger than our sun, that are moving through the galaxy at velocities that just make no sense compared to their surroundings. They're streaking across the sky.
So they didn't just drift away, they were pushed.
Kicked is more like it. The study focused on their binarity, whether they have a partner.
Yeah.
And that turns out to be the key clue. Most massive stars are born in pairs. They orbit each other. A binary system.
Binary system.
Right.
Right.
Now imagine one of those stars reaches the end of its life and goes supernova. It explodes. In a fraction of a second, a huge amount of mass is just gone. The gravitational tether that was holding the other star in place, it just snaps.
Like cutting the rope on a sling.
It's exactly. The survivor keeps its orbital speed, but now it's flying in a straight line. It gets catapulted out into the void. This study allows us to trace them back to the crime scene.
Ah, I like that.
By measuring their spin and speed, we can say, you came from that cluster over there and you were kicked out 5 million years ago.
So the galaxy is just full of these orphans speeding away from explosions?
It paints a picture of a galaxy that's so much more dynamic than we usually think. Stars aren't fixed points. They're projectiles if the conditions are right.
Which brings us to the real heavy hitters. We've talked about rocks and stars. Now we have to talk about the engines. The things that aren't just moving fast, but are making other things move fast.
The particle accelerators.
That November 16 report used the term microquasars. Now, I know what a quasar is. That's a supermassive black hole at the center of a galaxy, eating everything and shining brighter than a trillion suns. What's a microquasar?
It's a scale model. It's a binary system right here in our own Milky Way. You have a compact object, usually a black hole or a neutron star, orbiting a normal star.
Okay.
The black hole pulls matter off the normal star. That matter spirals in, gets superheated, forms a disk. But, and this is the crucial part, not all of it falls in. Some of it gets channeled by these intense magnetic fields and blasted out from the poles.
Jets.
The jets. And these microquasars are accelerating particles to speeds approaching the speed of light. The report calls them the galaxy's most extreme particle engines.
So it's like a natural Large Hadron Collider, but a billion times stronger, just sitting in our backyard.
Exactly. And because they're closer and smaller than the giant quasars, we can watch them change on human timescales. A quasar might take 1,000,000 years to flicker. A microquasar can flare up in a week. They're these perfect laboratories.
And we actually got a visual on this mechanism, didn't we? The M87 update.
Yes, hot off the press, February 6th. The Event Horizon Telescope team released new data on M87. That's the famous orange donut black hole we all saw a few years ago.
The celebrity black hole?
That's the one. They imaged it at a new frequency, 230 gigahertz, and for the first time, they saw the jet base.
Explain why that matters. We've seen pictures of jets before.
We've seen the black hole, and we've seen the long streak of the jet far, far away from it. But we've never clearly seen the connection point.
The launch site.
The launch site, where the event horizon actually launches the jet. It's like we've seen a fire hose spraying water, and we've seen the hydrant on the street, but we've never seen the actual nozzle where the water comes out.
And now we have the nozzle.
We have the nozzle, and it confirms that these things aren't just drains. I think that's a misconception people have, that black holes just suck.
Yeah, the cosmic vacuum cleaner.
But they're actually dispersers. That jet carries energy and matter across thousands of light years. It heats up surrounding gas. It can actually stop new stars from forming in a galaxy.
So the black hole is regulating the entire galaxy.
It's the thermostat. If the galaxy makes too many stars, the black hole feeds, fires a jet, heats the gas, and shuts down star formation. It's a feedback loop. Speed and violence are the tools the galaxy uses to keep itself stable.
That's a fascinating shift in perspective. The violence isn't accidental, it's functional.
Exactly. It's part of the system.
Now, speaking of things moving fast and not coming back,
Mm-hmm.
we have to talk about a departure. We have an interstellar visitor that's currently clocking out. Comet 3IS.
Ah, yes. The farewell tour.
We've had Oumuamua, we've had Borisov.
Yeah.
8TLS, Space.com reported on this just yesterday. What's the status?
It's leaving, but it is going out with a bang. NASA's infrared telescopes caught it dramatically brightening as it crosses the orbit of Mars and heads for the exit.
Well, why the flare-up? Is it exploding?
We aren't sure. It could be a pocket of volatile ice finally hitting the sunlight and just bursting, or the nucleus could be fracturing under the stress. But the real key is its trajectory. It's hyperbolic.
Which means it's not coming back.
Never. It's moving too fast for the sun to capture it. It fell in from deep space, swung by for a visit, and is now shooting off into the dark forever.
There's something kind of poetic about that. We just get this one brief glimpse.
It reminds us that the solar system isn't a closed box. Things drift through. If we aren't looking at the right moment, we miss them entirely. It makes you wonder how many we missed before we had these powerful telescopes.
Probably thousands. Just ghosts passing in the night.
And speaking of ghosts passing through, we have one last speed record to cover. The fastest thing possible.
Gravitational waves.
The ripples in reality itself, February 3rd. The detection of GW250113.
Not the catchiest name, but I hear it's a record breaker.
It is being called the clearest signal ever detected from a black hole merger.
Define clear in this context. What does that mean?
Usually, these signals are messy. They're buried deep in noise. But this one was just loud and sharp. It traveled billions of light years to get here, moving at the speed of light. And because the signal is so clean, it allows us to test Einstein's general relativity with a precision we've never had before.
We just keep testing that guy. Does he ever fail?
Not yet, but we're looking for the tiniest deviation. If the wave arrives a millisecond late, or if the shape of the ripple is slightly off from what the math predicts, it implies there's something else going on. Maybe quantum gravity, maybe extra dimensions.
So this wave is basically a letter sent from a collision across the universe, and we're checking the handwriting to see if gravity works the way we think it does.
And so far, the handwriting matches Einstein's perfectly, but we need these high-speed messengers to even ask the question.
So let's just look at the board here. It has been a crazy week for space news. We have got a house-sized rock spinning so fast it defies gravity. We've got stars being kicked out of binaries. We've got microquasars acting as particle cannons. And we found out our own solar system is driving through the cosmic fog 3 times faster than we thought.
It's a lot of kinetic energy.
It really challenges that idea of the still night sky. The universe is actually a high-speed engine.
And it brings me back to that solar system speed update, that 3x faster thing.
Yeah, I wanted to circle back to that. What's the final thought there?
Well, it triggers a provocative thought for me. If we were wrong about our own speed, our own reference frame until 2026, what else is skewed?
Right, because in that same batch of news, there was a mention of a new map of dark matter, the hidden structure of the universe.
Exactly. How do we calculate dark matter? We look at a galaxy, we measure how fast it spins,
Yeah.
and we say, there isn't enough visible mass to hold it together at that speed, so there must be invisible matter glue.
But that calculation depends entirely on measuring the speed correctly.
Yes. If our speedometers are miscalibrated, if we don't fully understand the relative velocity of the observer, which is us, versus the target, does that mess up the math on all the hidden stuff?
That is a heavy thought. We're trying to measure the speed of a passing car while we were doing donuts in the parking lot, and we just realized the speedometer in our own car is broken.
It might not disprove dark matter, but this week's reports certainly suggest we need to double-check our variables. The universe isn't just sitting there waiting to be measured. It's running away from us, towards us, and around us.
And it is up to us to keep up.
Absolutely.
Well, that's a wrap for this deep dive. If you feel a little more wind in your face today, just remember, it's the solar system racing through the interstellar medium at, well, a whole new speed. Keep looking up, keep asking questions, and try not to get too dizzy. Thanks for listening.
Thanks for having me.